Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry, Paper 3. In Unit 4, we will be studying about heterocycles Part 2. In the Lecture 2, we will be studying about imidazoles, synthesis, reactions and uses. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered in this session includes synthesis of imidazoles from substituted hydroxy substituted or halo substituted or amino substituted carbonyls. We will be looking at how imidazoles can be synthesized. From dicarbonyl compounds, Markov synthesis, Walsh synthesis, ring transformation reactions are some of the reactions we will be studying. And afterwards we will be studying about reactions of imidazoles, basically electrophilic reactions and nucleophilic reactions. Then finally we will be studying about the uses of some of the imidazole derivatives. In this session we will be studying about a 5-membered heterocyclic ring with 2 nitrogen atoms. So in the previous session we had studied about pyrazole derivative, which is 1,2-azole, and now we will be studying about imidazole, which is a 1,3-azole derivative. So it is again a 5-membered heterocycle with 2 nitrogen atoms, and it is having the sp2 hybridized and delocalized 6pi electrons of hetero atoms are present, and there are 2 nitrogen atoms are also present. So very similar to pyrazole derivatives what we have seen earlier. And we also know out of the 2 nitrogen atoms, the nitrogen which shares the lone pair of electron for the aromatic sextet formation is a non-basic one. That is, this nitrogen is the non-basic nitrogen, and there is another nitrogen which is a basic one, which due to which this imidazole behaves like an amine. And these are all the various resonance forms as shown here. Like the previous case, we also have 1, 2, 3 carbons where the carbanion is present, and there is one resonance form where the nitrogen is having a negative charge. So these are all the various resonance forms of imidazole. Let us look at some of the important imidazole derivative. Histidine, as shown here, is having an imidazole derivative, and clotrimazole, azomycin, and the purine, which is the nucleobase having adenosine, is also having the imidazole unit, and losartan is a drug which is generally used. So these are all the various compounds which are important imidazole derivatives. We will be looking at some of the important imidazole derivatives in the later part of our session. Let us now move on to the synthesis of imidazoles. Some of the reactions are given here from alpha substituted carbonyl compounds, and from dicarbonyl compounds, Walsh synthesis, ring transformation, and we also have many more synthesis methods which are not included here. These are all the 2 references from which some of the materials were taken. You can also refer these references for your additional information. Let us start with the reactions of alpha hydroxy or alpha haloketones with amidines. So this is the alpha hydroxy, the carbonyl unit is there, and hydroxy is substituent is present alpha to this one. So this is the alpha hydroxy derivative, and this is reacted with an amidine as shown here. Leads this reaction loses 2 water molecules to give the final product, the imidazole, as shown here. So in this particular case, the carbonyl unit has the R1 and R2 substituents as shown here, and the central carbon is having the third substituent, alkyl substituent. So that is present here. So this is how the condensation actually takes place. Let us look at the reaction mechanism of the alpha hydroxy or the alpha haloketones with amidines. So the initial step is the attack of the lone pair on the electrophilic carbon. So the nitrogen is having the lone pair, and the lone pair is attacking the electrophilic carbon with oxygen pulling the double bond pi electron towards itself. So we get this particular intermediate as shown here, and this intermediate loses water molecule, and then we end up with this ketoenol tautomers. Basically this is the enol derivative, and this is the ketone derivative. So we can get the ketoenol tautomers to exist as shown here, and this again undergoes a tautomerism, and the internal attack of the nucleophilic nitrogen on the electrophilic carbon takes place. So this is the crucial step which leads to the cyclization, and once this intermediate is formed, this loses water molecule, and we finally end up with the imidazole derivative. So here in the second step, as shown here, loss of water molecule takes place, and the cyclization step is a crucial step, which is the third one, where the attack of the nitrogen's lone pair on the electrophilic carbon takes place. So in this case also, there are two oxygen molecules present in the starting material, which are lost as two water molecules. So this is how here again we can also see the oxygens were lost as water molecules. So this leads to the formation of the imidazole derivative. And the next one is Markov synthesis. So in this particular case, the reactions of an alpha amino ketone happens with cyanides, thiocyanides or isothiocyanates. So this is the cyanide molecule shown here. So this is our amino ketone. So this amino ketone hydrochloride salt is there. Here the amino ketone is having a lone pair on the nitrogen. So this attacks this cyanide carbon and the triple bond carbon, and this undergoes various internal transfer of electrons, and then we end up with the cyclization happening at this particular step, which leads to isomerization of the thiol derivative, because in this particular case we are having, if we are using a thiocyanate or isothiocyanate, we will be ending up with the thiol derivative, and this thiol can be removed using treatment with Raney nickel or nitric acid. The next one is Debus-Radziwiłłski's synthesis. So in this particular case, a glyoxal is reacted with the formaldehyde in the presence of ammonia to give imidazole. This is an unsubstituted imidazole. So if we are using unsubstituted glyoxal, and that means dialdehyde, and formaldehydes were used, then this leads to the formation of imidazole. It is actually a two-step process. And in some cases we can also use a dicarbonyl compound instead of hydrogen. If we use alkyl group here, then it is nothing but a dicarbonyl compound, which is a ketone, and an aldehyde can be used here with instead of formaldehyde we can also use a substituent here, which is any aldehyde. So in that particular case we will have a substituted imidazole derivative will be formed, and this is basically a two-step process. The first step is the formation of the diamine. So that is what happens here, and the second step is the reaction of that with aldehyde. In the final step, water is lost. So in the two-step process, the first step is formation of the diamine, and in the second step the diamine undergoes reaction with the aldehyde to form the final product. So water is lost in this particular case. The next one is Bredrek-formamide synthesis. In this reaction, an alpha diketone or alpha hydroxy or alpha halo or alpha amino ketone is reacted with two equivalents of formamide. So this is the starting material. When X is OH halogen or NH2, so this is the hydroxy halo or amino ketone, and we can also use dicarbonyl, that is diketones can also be used with formamide. So this is the formamide. So 2 units or 2 equivalents of formamide is used in this particular reaction. This leads to the formation of substituted imidazole. So in the case of the formamide is basically the C2N3 fragment and the N1. So all these 2 fragments come from the formamide unit, and the rest of the carbonyl compound is shown here in the red color. So the carbonyl unit is the red one shown here, and the formamide is the green one shown here. So that way we can easily differentiate how each components are involved in this particular reaction. So this procedure is basically employed for making imidazoles unsubstituted at 2 positions. So that means this carbon is actually having a hydrogen. In other words, this carbon, whatever we are going to get is a unsubstituted one. So for making the 2 position unsubstituted, this is the best method to use. And if you look at the mechanism for this reaction, so we are taking either the dicarbonyl compound or the hydroxy amino or the halo derivative as shown here. The initial step is a reaction with formamide. So here the formamide reacts with one of the carbonyl unit which gives this particular intermediate, and the second molecule of the formamide again reacts to give this intermediate, and this loses water molecule to give the alkane derivative as shown here, which loses formic acid through cyclization to give the cyclized imidazole derivative. And the next one is a Walsh synthesis. In this particular reaction, NN disubstituted oxamides as shown here is reacted with phosphorus oxychloride. So this leads to the formation of substituted N substituted imidazoles. There is a halogen atom present here. This halogen atom can be removed by reduction reactions, basically treatment with LAH or other strong reducing agents removes this halogen. That leads to N substituted imidazole derivatives. If we look at the reaction mechanism, so the reaction mechanism is given here. So various steps are involved in this particular case. A diimine is formed in the first step, and which is in resonance structure as shown here. The internal attack of the nitrogen's lone pair happens on the alkene carbon, which leads to the concomitant loss of the halogen, which is a very good leaving group, and then the cyclization is happening at this particular case, leading to this particular intermediate, and loss of a proton and movement of electrons leads to the final product. And here we have the halogen, as I mentioned earlier. This halogen can be removed by treatment with lithium aluminum hydride or other reducing agents. The next one is from aryl aldoximes or propiolate esters. So aryl aldoximes, when treated with propiolate esters, gives substituted imidazole derivatives. So that is what is given here. If we look at the reaction mechanism, the entire reaction mechanism is shown here. This reaction actually involves a 1-3 shift. So this 1-3 shift is very crucial. After the 1-3 shift only, the internal cyclization takes place. The rest of the reactions are very similar to the previous one. And this loses water molecule in the final step to give the final imidazole derivative. So here what the transfer happens is nothing but Claisen rearrangement. So in this Claisen rearrangement, the initial formed intermediate rearranges through 1-3 shift to give this particular intermediate. This is nothing but an amidine derivative. So this amidine, there is a lone pair of electrons on the nitrogen. So this attacks the carbonyl. So this is the cyclization step, which leads to this hydroxy derivative. And this hydroxy derivative loses water molecule to give the, because the driving force for the loss of water molecule is the extension of conjugation. In this particular case, we have a carbonyl unit also here. So due to the extension of conjugation, this dehydration takes place very effectively. And then reactions of 1,2 diamino alkanes with acids. Carboxylic acids, when treated with 1,2 diamino alkanes at a very high temperature, leads to the cyclization as shown here, which gives with the palladium or alumina, palladium on alumina leads to substituted imidazole derivatives. And we can also make imidazoles by the ring transformation reaction. In this particular case, we had shown oxazole is converted into imidazole. One of the oxygen from this heterocycle is converted to nitrogen. So this reaction actually occurs at a very high temperature. Another reaction is a ring contraction reaction. Here pyrazines are converted to imidazoles. So here a strong base sodamide or potassium amide is generally used in these kind of reactions, and ammonia is used as the solvent for this particular transformation. And the next one is Van Leusen imidazole synthesis. So in this particular case, an aldehyde, amine and isocyanate are reacted to give imidazole derivatives. So this is the intermediate which is formed by the reaction of aldehyde and amines, and this is reacted with isocyanates. So this isocyanates and this imine both react together in the presence of paratoluene sulfonic acid to give substituted imidazole derivatives. The tosyl isocyanate part is actually shown here in the blue color. So this part of the molecule comes from this tosyl isocyanate derivative, and the aldehyde and the amine part are involved in this particular area. These units are coming from aldehyde and the imines. This is basically a multi-component reaction. In other words, we have aldehyde, we have amine, we have isocyanide. So we have three different compounds are involved in this reaction. So this is called as a multi-component reaction, and it is basically a 3+2 cycloaddition reaction. So that means 3 units comes from one of the compound and 2 units come from the other compound. Basically the aldehydes, that is they are formed from the reaction of aldehyde and amine is reacted with tosyl MICs isocyanides as shown here, and this reaction happens on the isocyanate carbon, which is highly reactive, and there is an active methylene and a leaving group. So the aldehyde and the imine part forms the 2 component, and the isocyanide forms the 3 component. The next one is the McQueen synthesis. In this case, imidazole 4,5 dicarboxylic acids are synthesized from 2,3-dinitrosuccinic acid. So the 2,3-dinitrosuccinic acid is shown here. This, when reacted with an aldehyde in the presence of ammonia, leads to the formation of substituted imidazole. Here we have the 4,5 position substituted with carboxylic acid unit. So this is a dicarboxylic acid unit. But this method is a very old method and it is currently not frequently used. Then let us look at the reactions of imidazole. So the first one, we will look at how imidazole can undergo tautomerization. Imidazole, the unsubstituted imidazole actually undergoes tautomerization very rapidly. In other words, we say two identical tautomers with a rapid exchange of proton between two annular nitrogen, that is NH and the double bond N, happens very rapidly. So that is the reason we can never isolate any one of these tautomers in the case of unsubstituted imidazoles. But when we take asymmetrical imidazoles where we have one alkyl substituent that is present, then this leads to a very interesting phenomena. So in this particular case, when the tautomerization takes place, what we are going to end up with the 4-alkyl imidazole is actually converted to 5-alkyl imidazole. The reason is the NH nitrogen is given the numbering first. So when we have to number this alkyl substituent, we go from 1, 2, 3, 4. So the 4th carbon is having the alkyl substituents. Whereas when this undergoes tautomerization, the hydrogen shifts from the nitrogen number 1 to this nitrogen. In other words, now this becomes the number 1 but then the second nitrogen has to get the lowest number. So the numbering will start from 1, 2, 3, 4, 5. So this carbon now becomes the 5 substituted one. So in other words, whenever there is a imidazole having this type of substitution, tautomerization actually shows that it is generally called as 4 or 5 alkyl imidazole, because this numbering is going to be very complicated. This happens only if this nitrogen, the imidazole nitrogen, is unsubstituted. Provided there is a proton on this nitrogen, then only this kind of tautomerization takes place. And this interconversion is so fast that it is very difficult to isolate any one form because of the rapid proton transfer. So this is the one thing we have to remember when we deal with the imidazoles. When we deal with imidazoles, and if the nitrogen is having a hydrogen, that means there is not substituted, then this kind of tautomerization is possible. And due to this, we have to identify what are the consequences of this kind of tautomerization on reactivity on imidazole. So here, if you look at the imidazole structure, the nitrogen is having a proton, a hydrogen here. So this is the most acidic hydrogen, and because of this acidic nature, this nitrogen can be attacked by nucleophile. And we have other carbons. We have carbon number 2, carbon number 4, and carbon number 5. So they behave differently because of the nitrogen atoms that are present here. So we can exactly say that the electrophilic attack actually occurs on the N3, that is the pyridine type, because this is a basic nitrogen. So an electrophile can easily attack this nitrogen more effectively, but not on the NH nitrogen. So that is the reason this pyrrole nitrogen is not attacked by the electrophile, whereas the pyridine nitrogen is easily attacked by the electrophile, because this lone pair of electron on the nitrogen is actually involved in the aromatics pi sextet formation. So that is the reason this nitrogen is actually electron deficient. So the electrophile cannot attack this pyrrole type nitrogen. The same way, if you look at the neighboring carbons, these two carbons are actually electron deficient, and due to which these two carbons can be attacked by the electrophile very readily. The carbon number 4 and 5 are electron rich compared to carbon number 2. So because of the rich electron density on carbon number 4 and 5, the electrophile attacks either 4 position or 5 position, whereas this carbon number 2 is electron deficient because of two adjacent heteroatoms pulling electron towards themselves. So this carbon becomes more electron deficient, so the nucleophile can attack the C2 carbon very effectively. In other words, we can say the attack of the nucleophile generally takes place on carbon number 2 or nitrogen number 1. And of course, imidazole as such shows amphoteric nature. Now let us look at the electrophilic reactions of imidazoles. As we have seen, the imidazole is substituted at N1, that is, if the nitrogen is substituted, then the electrophilic attack takes place effectively on the third carbon, that is N3 forms very direct electrophilic attack. So here we have an alkyl halide which reacts with the imidazole, where the pyrrole nitrogen is substituted. This leads to the N3 substitution happening very effectively. That is, the alkyl group adds to the pyridine like nitrogen, and this also forms the quaternary salt. If we take an unsubstituted imidazole, that is, the nitrogen is having a or the hydrogen, then in that case reaction with an alkyl halide actually leads to the product or the alkylation taking place on the nitrogen itself, because this compound basically is formed through the N3 alkyl imidazolium cation, because we know this nitrogen is electron rich, so the alkyl cation can attack this carbon very effectively, which leads to this particular cation formed, and this is in resonance as shown here. And loss of proton, that is the base abstraction of the proton, leads to re-aromatization as shown here, which leads to the product in which the pyrrole nitrogen is substituted as shown here. So this is a reaction which is different from the previous case, where the nitrogen is already having alkyl substituent. The 3 substitution takes place at that reaction. When the nitrogen is having only hydrogen, the alkylation takes place on the N1 only as shown here. So if we look at the overall reaction, the alkylation of the imidazole, especially the free NH group, produces protonated N-alkyl imidazoles, which can be deprotonated by the base, that is imidazole itself. So when it is unsubstituted imidazole, this acts as the substrate and also this acts as the base. So both the things are done by the same imidazole itself. So that is what here we had shown. The base acting on this one is nothing but not an external base, but it is the imidazole itself acting as a base. So the initial step is the electrophile, that is the carbocation attacking the pyridine-like nitrogen, which leads to the cation formation as shown here. So this is the N3 alkyl imidazolium cation that is formed, and this is existing in the resonance form as shown here. And this proton is basically abstracted by the base, that is the imidazole itself abstracts this proton, and this leads to the nitrogen substituted imidazole. In other words, the pyrrole nitrogen gets converted into pyridine nitrogen. So that is what is happening, and the pyridine nitrogen on which the alkylation took place now becomes like a pyrrole type nitrogen. So the internal exchange happens within this molecule, and that is what actually happens in the electrophilic substitution reaction. And instead of the actual 3 substituted one which should be formed, we are getting 1 substituted one as shown here. Then there is another reaction which is reaction with the acid halides. So in this particular case, when we react imidazole with alkyl acid chlorides, so the free NH group is the one which undergoes N-acylation, and basically the solvent used is generally ether or some inert solvents are used, and the reaction can be carried out at room temperature. This leads to the formation of N-acyl imidazoles. Again, in this particular case also, the intermediate is the N3-acyl imidazolium cation. So the initial attack of this electrophile happens on this pyridine nitrogen, and a base abstracts the proton from the pyrrole-like nitrogen, which leads to the formation of the final N-acyl imidazoles. So here again what we see is one of the nitrogen getting converted to the other one. So that means the pyridine, the substitution happens on 3 position, which gets converted to 1 position after the base abstraction. Then let us look at some other reactions of the imidazole, because imidazole is an excellent nucleophile, and it catalyzes hydrolysis of esters or acid derivatives. So this is the reaction as shown here. The hydrolysis of the ester happens with the help of imidazole. The various steps are given here. So initially the reaction, as we already know, the electrophilic attack happens on the pyridine like a nitrogen. This is the first initial intermediate which is formed, that is the N-acyl derivative, and this N-acyl derivative loses proton to give the imidazole derivative as shown here. This on hydrolysis gives this RCO bond is cleaved, and the imidazole is regenerated, along with the formation of the carboxylic acid. So this is what is the overall reaction, and in this reaction imidazole hydrolyzes the esters very effectively. So the overall reaction, what we can say is a carboxylic ester or the acid derivative is converted to carboxylic acid by treatment or reaction with imidazole. Then let us look at the electrophilic attack on different positions on the imidazole itself. We have attack on C2. We can also study the attack on C4. We have another place at C5. So between all the three places, what is the most preferred site of attacks? Let us look. If you look at the attack happens on the C2 position, because we already know this carbon is already more electron deficient. That is the reason electrophile cannot attack this position, which we already know, but we can also confirm that by writing some of the intermediates. So when we write this particular intermediate, the electrophile adding to the C2 carbon leads to a highly unstable intermediate, and this is the most unfavorable intermediate, due to which this reaction does not occur. In other words, what we can say is C2 attack of electrophile does not take place. And if you look at C4, we have a couple of resonance stabilized structures. So this is a possible case where electrophile can attack C4. And when we look at C5, we have more resonance structures which are stabilizing this particular intermediate. So when we compare between C4 and the C5 attack, we can clearly say C5 attack is the most preferred one because of the various resonance structures that are possible. And of course, the reaction conditions and the nature of the electrophile also decides where the reaction will actually take place. So here we have some of the electrophilic reactions of imidazole. So in this particular case, the major product that is formed is the 4 substituted one, that is the nitration takes place in the 4th position. Similarly, sulfonation and acylation both, in the case of sulfonation it happens at the position 4, whereas when we talk about acylation, this acylation actually happens at 2 position. Now we will have to see how a 2 position attack actually takes place in this particular case, because as we have seen earlier, if this is a electrophilic reaction, then this C2 carbon is not favorable for the electrophile to attack, but we are also getting, especially when in the case of bromination, the C2 position is also attacked by the bromine. So how the reaction actually proceeds? So in this particular position, the 2 position attack for the bromination is explained based on the nucleophilic attack. So in this bromination reaction, bromonium ion is not the one which attacks this carbon. It is the bromide ion which is present in the medium that attacks the C2 carbon. So that is how the nucleophilic attack takes place, which again leads to the formation of bromo derivative. So how we can confirm that is when we react the imidazole with cyanogen bromide. Cyanogen bromide generally gives a bromide ion which is a nucleophile. So that nucleophilic reaction leads to 2 bromo derivatives of imidazole. So that clearly tells that if a C2 position has to be attacked, then the reaction has to follow a nucleophilic attack mechanism and not the electrophilic attack. So here we will see more examples of the nucleophilic reaction. So in all the cases you can see if we are using primary amines, the bromine can be replaced with the corresponding amine. So this leads to the nucleophilic attack on this 2 carbon. But when we have a cyanide, because chlorine is the leaving group here, so due to which the attack actually happens on this particular carbon only. Although this carbon is unsubstituted, the leaving group is present only on this carbon. So in this particular case, the nucleophilic attack happens on the 5th position when we treat the chloro derivative with the potassium cyanide. The cyano derivative is formed. And when we take the imidazole, N substituted imidazoles, the 2 position proton can be abstracted by a strong base like butyl lithium. So this leads to nucleophilic substitution. When we treat this anion with alkyl halide, the two substitution takes place, and when we treat with the carbon dioxide, the end product is a carboxylic acid, and when we treat with the DMF, the formyl derivative, that aldehyde, is formed. So these are all some examples of the nucleophilic reactions of imidazole. So this happens exclusively on the C2 position. And then let us look at the C acylation, because earlier we had seen in the acylation reaction, the acylation takes place on this particular carbon. How the reaction actually proceeds, it is not a simple reaction mechanism which can be employed to explain this product formation. So the initial reaction happens on the N acylation only. So this pyridine like nitrogen is the place, because this nitrogen, the pyrrole nitrogen, is already having an alkyl group, so this is blocked. So this pyridine like nitrogen only is can be attacked by the electrophile. So this electrophilic reaction first happens, or the attack of the acid chloride happens on this nitrogen. So the initial N acylation takes place, and then it is followed by the, because we are using a base here, triethylamine base is used in this reaction, which deprotonates the C2 hydrogen. So this C2 hydrogen is removed by the base. Then the 1,2 shift happens from the nitrogen to the carbon. The 1,2 shift of the acyl group takes place. That leads to the final two substituted product. So even though it looks as if the C2 carbon is not prone for an electrophilic attack, this reaction is possible because of the intermediate that is formed, and the reaction also is running in the presence of a base. So for the C2 acylation, we need a base for this particular reaction to be successful. Let us look at some of the important imidazole drugs. So zolpidem is the trade name for zolpidem is Ambien. So this is medication which is primarily used for short-term treatment of sleeping problems. So this has a imidazole moiety as shown here, and ketoconazole, which is the trade name is Nizoral, is a antifungal medication that is used to treat a number of fungal infection. The structure of the compound is shown here. This is having the imidazole moiety as shown here. There is also another drug, pentostatin. This is an anti-cancer chemotherapeutic compound. This has the imidazole moiety as shown here. The next one is temozolomide. The trade name for this compound is Temodor. Is a drug which is used to treat some brain tumors such as glioblastoma multiforme or anaplastic astrocytoma. So this compound also has a imidazole unit as shown here. There are other compounds like cimetidine, which is a histamine H2 receptor antagonist, and this inhibits the stomach acid production, and this is mainly used for the treatment of heartburn and peptic ulcers. And vardenafil, so this is very similar to Viagra. This compound name is Levitra. So this compound is also used for the erectile dysfunctions, and this is a PDE5 inhibitor, and this is used for erectile dysfunction for the treatment. And we have losartan. This is a drug which is used to treat high blood pressure, and it is also used for the diabetic kidney diseases, heart failures and other things. It is used as a drug. And then we have nilotinib, and this is a drug used for the treatment of chronic myelogenous leukemia, which has a Philadelphia chromosome. So this is a very specific drug which is used specifically for treatment of CML. Let us recap what we have studied so far. We have studied so far about the synthesis of imidazoles. We have studied about how hydroxy, halo or amino carbonyls can be converted to imidazoles. And we also have studied about how dicarbonyl compounds can be converted to imidazoles. Markov synthesis, Walsh synthesis, ring transformation reactions are some of the other reactions we have studied in this particular session. Then we also have studied about the various reactions of imidazoles, focusing on both electrophilic reactions and nucleophilic reactions. And finally, we also saw lots of uses of imidazole derivatives. With that, we conclude this session. Thank you.